Okay, good. So you have your mic on?
Yes.
Okay. So now we'll have a talk by Mariami, who will talk again about causality in quantum networks. So the floor is yours.
Thank you. Thanks for the organizers for inviting me and giving me this opportunity to speak here. And I would like to also thank my collaborators. Actually, this is my second conference on causality. First one was in 2019 in Capri, where I met some of you. And I never worked on the subject before, and then we decided to work on it together on some topics that you will see here with Nikolai Miklin and Rafael Chavez. And we planned some nice trip to Brazil, but then you know all what happened. So this is all the work that was done online, but it had some positive. We could actually spread online and include more and more people throughout these years. So some of the people from Brazil that you see here, and like Georgie Moreno and Rafael, Nikolai works in Germany, and then there are some more people from Köln group that I was part of, and also Fabio's lab. I didn't write all the names, but Causal is here, so you can consult him on some experimental part. So my talk will be divided into two parts. I'm not sure I will manage to get to the second part, but let's see. So the first question that I'll be asking is something in the direction of correlation versus causation, and differently from how Robert advised us, I'm going to start from the classical case and go in the quantum and see what happens there. And as you might expect, many things won't go through, but then maybe we can use his expertise to understand at some point what really happens if you start coming from the quantum part. And the question that we'll be asking here is, can we tell if the random variable A causes the random variable B, and what is the strength of this causation? Okay, we want to measure this kind of causal influence. And the second question, yeah?
Can you just look on the chat, because I see two questions. I don't have it, just to check that they can hear you. It's fine, sorry.
Yeah, no problem. And the second question is in the direction of what Nikolai just spoke about, but it's more about understanding the causal compatibility. You have certain probability distribution given, it's some observed statistics, and you're asking whether it's compatible to some quantum network. So let me start from the first part. So let's start from the very beginning. So causal reasoning. This is something very old, very fruitful, very useful in many different areas like economics, medicine, physics now, and AI. And all starts from two variables, the simplest case. If you have two correlated variables, A and B, then you know that there must be certain causal dependencies between them. Either A is causing B, B is causing A, or you have a common cause, which is the unobservable common cause lambda, which is influencing both A and B together, or you can have something even more complicated. And the question that we are interested now is, let's say if the variable A, which I draw like a circle here, and the variable B, if there is such a causal dependence between them, and the causal dependencies are depicted with the arrows all the time in this talk, we want to not only say whether variable A is causing variable B, but we also want to measure how much variable A is directly causing variable B. And we want to do this independent of all the possible common causes. So we want to neglect all the common causes, but only speak about the direct causal influence. And classically, this theory of how to do this, or how to do such a measure, how to calculate the measure of causal influence, it's already well studied, and it's done through something called do calculus that you also mentioned, but it's under the interventions, the name of interventions. So what happens here is that if you want to measure direct causal influence from A to B, you have to intervene on the variable, a random variable A, and you have to force it take the certain value, independent of what was the relation between this latent unobserved common cause. In this way, you can convince yourself that you're erasing all the links, unobserved links that you might have no data of in your statistics. And then if you do this, you can define something called average causal effect, which is this measure of causal influence. And this average causal effect is defined in the following way, and I'll tell you in a second what is this notation here. But what it means is that you are observing of what is the probability of obtaining B if you intervened with if you did or intervened with the variable A with the value of small a, and difference if you intervened with a different value A prime. Okay, so and now you are taking this maximized difference, and if you see that this maximum is non-zero, then you can say that there is a non-zero direct causal effect from variable A to variable B. So these probabilities are called do probabilities, and they are very important in causal inference. And let me tell you now how they are defined, because later it's going to be useful when we generalize this to quantum. So what can we have here? In the beginning, I'm just writing the probability distribution PAB, which is compatible with this causal structure. And this probability distribution, it just factorizes in the way that causal structure dictates us, right? PA only depends on lambda, and B depends on A and lambda, and this is this latent random variable that we do not observe. Now the do probabilities, because we interfere on the variable of A, value of A independent of what was lambda, we can just take this probability equal to 1. Okay, and this is going to be our new do probability. And you can convince yourself that this is very different from the conditional probabilities, and they shouldn't be confused with one another. Because if you just, by chance, just take there the conditional probability, it will not tell you anything about the cause and effect relation. You will actually reach the Simpson's paradox there. So you have to really intervene and take this probability equal to 1. And let me just repeat how the average causal effect was then written. It's difference between the two possible do probabilities. Okay, so far so good. You can intervene. You can, let's say if A is smoking and B is cancer, you can force somebody to start smoking if their genetics was not telling them to do so. But you can also agree that this is not very ethical to intervene on the intervene in such experiments. And moreover, it might not be possible if you have the real world data, already collected statistics. You can no longer intervene, but you still want to use this data to reason about causal effect relations. And for this, people have come up with something called instrumental variable, which kind of substitutes the intervention. So it's quite a powerful tool. What it does effectively, you have one extra variable, which is called the instrument. It's in the full control of the experimenter, and it just controls one of the variables. And this is the variable A. And this was the variable that you indeed wanted to intervene on. So let's see what happens. So let's take the example of A again smoking, B cancer, and lambda is genetics, and X could be a taxation of tobacco. And we believe that this is independent of whether you develop cancer or not, and it's independent of genetics. But again, I use the word believe, and this is something very important in causal inference, how you choose your instrument in a nice way, but this is not the topic of today's discussion. Actually, it's an important question, and if you find a good instrumental variable for different statistical models, you might get very famous in different areas of science. Last year, actually, such results got a Nobel Prize in economics, just looking at the statistics in certain economical models and choosing the instrument in a nice way. But now, let's see how it helps us. So we can now have the statistics, conditional probability distribution, which very much looks like this Bell decomposition that you might know from the CHSH game, but it's different in the way that Bob doesn't have independent input. Bob's input is governed by Alice's output. You can also think of it this way, but this is just the conditional probability distribution decomposed according to this instrumental scenario. And again, this is a very important assumption that you cannot guarantee, but you believe that lambda is independent of X. And if you believe that you have a good instrumental variable, then there is a very powerful result that using just from the probabilities or from the statistics, in the binary setting that we are going to be focusing on, there are results also for more general settings, but in the binary settings, you can actually use just the observed statistics to lower bound this value of average causal effect. Okay, so you no longer have to do the intervention and take the difference, but you can say that there is at least this much causal influence between A and B. And this is the result from Balka and Pearl, and it's, again, very influential, but let's see now how it propagates to quantum mechanics. And this is going to be the main point of the talk. So what I'm going to be doing is what Robert told us not to do, and I'm going to be just taking the classical common cause, and I'm going to be replacing it with the quantum common cause. But let's see what happens. So here I'm going to be defining the quantum instrumental scenario. And quantum instrumental scenario is not, again, very much different from the quantum CHSH game, if you know like most of you will recognize. What we have here is that we have a shared quantum state. And these random variables that you see here are produced as a result of POVM measurements. And accordingly, you can write down the joint probability distribution, where you have Alice has input, Bob also has input, but Bob's input is governed by Alice's output. Okay, again, you have just joint probability distribution of this form. Now, if you look at how this probability distribution differs from the one you could obtain in the set of correlations differ from something you could obtain in the classical one, whenever rho AB was just a classical random shared randomness, these two coincide. And this is not very surprising from the CHSH scenario, because A is giving, there is no freedom of choice for Bob. A is giving her output to Bob. So the set of correlations coincide. So in this particular instrumental scenario, if you had a quantum state, there would be no Bell inequality for you to test that you indeed have an entangled state or you had incompatible measurements. However, we will try to convince you that you can still device-independently test quantumness if you do not try to violate a Bell inequality, but if you try to violate certain causal inequalities. And that's where I'm taking the talk towards. So in order to do that, I have to explain you how one does the do probabilities in the quantum setting. So if you remember, these conditional probabilities looked something like this, where you had a common shared state, and we were making the measurements on Alice's and Bob's side. But now we want to intervene on the classical variable, okay? So this is the intervention of the classical, on the classical variable. So what it means is that Alice could be making the measurement, but she throws out her measurement output, and we intervene on this classical data. And accordingly, how this is represented in the quantum do probabilities, and you can imagine to distinguish that there should be a subscript Q here, is that we have identity on Alice's measurement side, and only Bob is doing the measurement, according to the variable A that we intervened on. And now this is quantum do probability. This is how it was defined. Some people are unhappy with this definition. I was unhappy with it myself. And now we are trying to generalize it slightly to more general case, when you don't only intervene on the classical data, but you try to intervene on actual instrument or something more general. You allow certain channels there. But this is something that is ongoing research, and it's not in the current talk. But no matter how you generalize this definition, it should collapse to this particular case whenever you intervene on classical data. So it still has its merit as it is written on a slide. So now what we can do is that we can define quantum average causal effect. And it's, again, the difference between two do probabilities when you intervene with variable A with the value A or A prime, and you take a difference, and this is something you call quantum average causal effect. Now, what's the first claim that Raphael noticed with his collaborators is that the lower bounds that we had from Pearl, these well-celebrated lower bounds, obtained from the statistics, they actually no longer hold if we have the quantum shared state. And this was surprising to them because it seemed like correlation set was exactly the same. But now if you're considering lower bounding average causal effect, then it seems like something else is going on. And to see this lower bound doesn't hold, it's a very simple task. What you can do, you can take a Bell state as rho AB. And because we are not doing anything on Ali's side, you can consider that you are tracing out the first party. And we know that if you have a Bell state and you trace out the first party, all you get on the Bob side is the identity over 2. And now if we insert this in average causal effect, quantum average causal effect, as long as trace of these two expressions are equal to each other, you will get that average causal effect is always 0 for, let's say, projective measurements and the Bell state. However, I haven't told you about what are the measurements of Alice, what are the actual measurements of Bob, and you can easily go ahead and make these statistics here on the right-hand side of the inequality positive number, strictly positive number, and then you will get that 0 is greater or equal than some positive number, and this way you will violate this causal inequality using a quantum state. So then this brings me to the key points. What was known in this Capri conference that we joined, that Raphael told us that even though the set of correlations coincide for lambda and rho AB, that causal dependencies seem to be very different. And then we started to ask the questions similar to what's already known for the Bell states, a Bell scenario. Then if we know that there is this one violation, can we actually understand which other states and measurements give us similar violation? And we know that there exists a classical lower bound, and we also know that it's violated by quantum states, but can we actually have a quantum lower bound, which is going to be valid for the quantum experiments? And the first result in this direction is very similar to what you have from the CHSH scenario, is that every pure entangled state can generate correlations that violate classical bound on average causal effect. And moreover, entanglement is necessary but not sufficient for such a violation. So necessary part is very easy to see, and the fact that it's not sufficient, that's also not so difficult to observe. Something different from the CHSH scenario is that the maximum violation that you see here, so here is a curve of violation with alpha, and alpha is a parameter in the 2-qubit entangled state. Maximal violation is not achieved for maximally entangled state, but it's for some other state. But this is not surprising to me because the inequality we started from was not symmetric itself, so there was no reason. You can think of it as self-testing this state. I mean, you can also self-test any non-maximally entangled state, so it goes a bit in that same direction. The second question that we answered concerns measurements, that every pair of incompatible rank 1 projective qubit measurements can generate correlations that violate classical bound of this causal influence. And moreover, incompatibility is necessary but not sufficient. And here you have a similar curve. I don't know if you, oh yeah, it's nicely visible. Here it's more blurrier. So you have the similar curve of incompatibility, and you see that this incompatibility angle that is characterized by this measurement, it's not maximally incompatible measurement, so it goes in the same direction as, again, self-testing of non-maximally incompatible measurements. The third result, and much harder to prove, was to come up with the valid quantum bound. So this is now, if you have a quantum experiment and you know that your statistics are obtained from the quantum test, so this is some ugly expression that we obtained after trying for a very long time. And this is the valid lower bound if you have a quantum average causal effect. And we took even more time to find the place where this lower bound was non-trivial. So we either got something negative because we have 2 minus signs here, or we got 0. or we got that it exactly coincided with the classical lower bound. So it was like a witch hunt kind of a thing. At some point, we believed that we couldn't derive anything like this, but here you might see a nice slice of correlations that we have obtained, for which you can see that this is classical non-zero lower bound, the blue region. This is the quantum one, which is obtained using the following expression. And this dashed line in this slice are non-signaling lower bounds, which I don't present here, but you can read it in the following paper. But literally, this is like weeks of search of slices and using SDP hierarchies, and we couldn't find any better slice, for example. And this is motivating to think about how to derive the better ones. At the moment, we have no ideas how to get the better lower bounds for the quantum average causal effect, but we still want to work on it, and if some of you are interested, we are very happy to discuss. So result 4 is the experimental collaboration, and we did this with the group of Fabio, and Gonzalo maybe will talk about it a bit on Friday. This is the results of the experiments that they did. This is the curve where you achieve certain violations. So these are the theoretical results with the experimental results. And so this is just seeing that you can actually indeed reproduce the same curve. But for me personally, the right-hand side is more interesting, where we have 3 different curves. This is the statistics gained for the actual classical lower bound of average causal effect. This is the violation that theory predicted that quantum average causal effect will give us. And this is the intervention part, when we did the intervention on the quantum experiment. This is the theory part and the experimental dots. And this is the quantum non-trivial lower bound. And again, you see that region is not from alpha is equal to 0 to something else, because this kind of a nice plot only happened in very particular region. But this is not the weakness of experiment. Experiment coincides very nicely with the theory, but this is the weakness of the theory, that we don't know what happens in the outside of this region, or we don't have better lower bounds. And the last result in this direction is something motivated also from this. We were working on it when this Nobel Prize in economics was announced, and this was motivated a bit from the results there, because we saw that there was an exact overlap of what we are doing in quantum, and we thought maybe let's try to use some of the methods we know and some people from causal inference might not be using. And this is the causal inference with imperfect instrumental variable. So this is truly classical case, and what happens is that x and lambda might not be independent of each other, and in many cases, if you consider the example of A being going to the college and B is your earning in the future, people have taken as an instrumental variable something like how far you live from the city with the college in it. And later on, they indeed deduce that going to a college gives you better earning in the future, but how far you live from a city is not really independent of the common cause, which is something like how much your parents earn. So this kind of the dependencies, if you have lambda is something that you didn't observe, the common cause of how much your parents earn could have a direct influence of where you actually live or how far you live from a city. And in this case, if you have such a dependence, the question is, should you throw away all your data, or can you still use the statistics? And this is what we tried to aim here, and this is again fully classical result. We tried to introduce, we tried to work with the measure of the dependence between x and lambda, and we have the results that we analytically derive the minimal measurement dependency required to explain certain violation of the lower bounds on average causal effect. And you can also ask the same question when it comes to quantum violation. Like if you have a certain amount of quantum violation, how much measurement dependence would you actually need to explain such a violation? Maybe you did something wrong in your lab and you don't actually have a quantum state there. And more generally, one can actually give an any linear valid inequality for binary instrumental scenario, one can analytically derive the adapted inequalities in terms of measurement dependency. That if you are threatened or you are not sure that you have certain amount of dependency between lambda and x, you can actually then make your inequalities looser and work with those inequalities instead of starting from the one that you are fully agnostic about lambda. And this actually concludes the first part of my talk. And if I don't have much time, I'm happy not to move to the second part because it's also about the lunchtime. So let me first conclude this. These are our results that connect about cause and effect relations. That we try to argue that causal reasoning is very different in quantum mechanics than from the classical case. And we have the violation of classical bound on average causal effect, and this can witness the device-independently measurement incompatibility and entanglement. And this is, in a way, surprising because in such a scenario, when you have two inputs and two outputs, you cannot have any violation of Bell inequality. And we had hard time, but we somehow managed to have very loose bounds on average causal effect on quantum common cause. And we also collaborated with the experimentalists. And finally, we talked about some imperfect instruments fully in the classical case. So there are a bunch of things to do in the future. First is, as I mentioned, how to get the quantum lower bounds, which are better than what we have. And this is even more pressing when you have more inputs and more outputs, because there things go really crazy, and then maybe there is more venue to have better lower bounds, but still it's very enchanted territory. And for more inputs and more outputs, there are certain classical inequalities, but we have not discussed their violation in the quantum settings. And what I'm most passionate about is that more generalized framework for quantum interventions. The two probabilities that I presented, I'm not 100% happy with this definition. I would like to see more general definition, and this is something that we are working on. And this we discuss, and we haven't reached a good one yet. Otherwise, I would definitely share it already with you. But if you have some ideas or if you hate this definition, it would be a good time to join the forces. And with this, I could either say thank you, or how much time do I have?
15, 20 minutes.
Oh, okay.
Including questions.
Okay. I have a shorter part, which I can go faster. It's... But if you have questions, I can also stop here and see how far we go, and we can also go for lunch earlier.
Okay, let's do it like this. So, Is there any question, or what is next? Maybe you should say it.
It's inflation hierarchy, convergent inflation hierarchy. Yeah, there are
So
questions.
if we take question now, we may not have time for the second part. So I don't see any strong opinion. I suggest you try to go.
He had one question. Okay. Then, sorry for... I'm back from a vacation 2 days ago, and I didn't know I have a talk today, so I crammed two things together. But let's see. I don't think it's going to be longer than 15 minutes. And Nicola gave a very nice introduction to all the networks, so I can kind of use that. The second part is a more easier question. It's about causal compatibility, but it has actually harder solution, I think. The causal compatibility question is that I have probability distribution given over observed variables A, B, and C. And the question is, can you give me the P of EM elements on Alice's, Bob's, and Charlie's side, and 3 independent sources, which reproduces these correlations? So that's a big question, and he already tried to motivate this in the last talk. And we define a bit more looser problem, which is approximate causal compatibility problem. You have a given epsilon, which is greater or equal to 0, a causal structure, and the probability distribution P over observed random variables. Determine whether there exists a distribution P tilde that can be produced by a quantum description of the causal structure such that this original probability distribution and P tilde are not far from each other. And our main result, if we don't go very far, is that there indeed exists a hierarchy of semi-definite programming relaxations for the approximate quantum causal compatibility problem, which is complete in the sense that it can detect any incompatible distribution with measurement operators of a given Schmidt rank R. And this is the drawback. We don't answer it generally. We say that if you restrict your Schmidt rank R, we can solve this problem with this converging hierarchy. But on the other hand, every compatible distribution P can be arbitrarily well approximated with a finite Schmidt rank. So if you let the Schmidt rank go to infinity, you can solve the problem entirely. But now this is, if you know the inflation hierarchy, this is introducing yet another parameter for which actually writing the program and doing the entire hierarchy yourself would be hell. We tried, was not fun. But there are few challenges in this direction, right? So the first challenge that you have in the causal compatibility, that Nikolai introduced it very well, that you have a non-convex set. And if you want to use the STP hierarchies, if you want to request that your sources are independent from one another, you cannot really put this as a constraint in your STP. This is a nonlinear constraint, so somehow you should linearize this independence. And luckily, this is doable using something called inflation. Many of you have seen it. Some of you came up with it. So what happens here is that if P is compatible, there exists an inflated causal structure with n copies of these systems. I just took the copies of these systems and n square copies of the P of EM elements, such that it should be independent whether you measure this state and observe statistics, or you measure these states and observe statistics. And thanks. These permutation symmetries, luckily, you can include in your STP, and these are the linear constraints. And from these symmetries, this is at least how it happens in the classical case, using certain definite theorems, you can actually imply the independence or get later the independence of the sources. So this is also a hope in the quantum inflation, but this is something that was conjectured that it's going to work, and here we try to show that it might not entirely work, but if you twitch the hierarchy a bit, then you will reach the solution, convergent solution. And the idea is, again, to use all these symmetries as your constraint in the STP. Let's look at the STP a bit more in detail. So how it would work, you have the hierarchy of semi-definite programs. For the triangle scenario, you have three outputs of the probability distribution, and you also input n, which is the level of inflation, how many copies of the latent quantum states you want to take. And the output is that there exists or does not exist the operators and the state rho on their algebra, such that rho has permutation invariance like we requested. And indeed, whenever we make this P of EM effects on this state, you get the probability distribution. But this STP just tells you that there exists such a rho. It has not argued that rho is separable or anything in this direction. Okay? It just tells you that such a symmetric state exists. But now what we have to do, even though it is now an STP and it's convex, it concerns the convex set, we have, using symmetries, convexified the problem, but we have to still talk about some kind of an independence between sources. And we have to use these symmetries to get to that independence. So we have to say that this rho factorizes, right? It factorizes according to the certain cut on Alice's side. And this turns out to be a very difficult problem. How to say that I have a joint P of EM given, I have joint effects given, but I want to say that the state rho is something tensor something, but I cannot even say that anymore because we know from the Sirelson's problem that you cannot even say the tensor product as freely for the finite dimensional cases as you had it before, because we know now that there is different notions of tensor products that you have to be worried about when talking about the compatibility problem. So because you might be looking for the infinite dimensional states here rather than the finite dimensional, and then you have to consider algebraic tensor products or maximal tensor products instead of the usual ones that you learn in the elementary quantum mechanics classes. And more clearly, we want such a factorization to happen that whenever we take a state, we want our SDP to give us the result, positive result, when there exists a state which factorizes between left or minus and plus cut of this vertex. But again, we are only given these P of EM elements. And I've already summarized this. There are few to-dos. We have first to-do is that we want to have a converging SDP hierarchy, and this is taken care. There exists certain NPO, non-commuting polynomial optimization techniques that you can use. But there is a second problem that you want to use these symmetries in order to translate to independence, and there are these definite theorems which do this. But existing shelf-definite theorems only worked for separable Hilbert spaces. So they worked only for the mean tensor product. They didn't work for the ones that we needed, but luckily you could take the older results from Raggio and Werner and generalize to the max tensor products. And that's the one that we were working on. So I'm not going to go into details here, but a significant amount of work went into this direction to come up with the new definite theorems and get the independence. And the final result, even if you have this independence, you have to say, where does this independence live? Like, again, you are given the full P of EM element, but what is minus and what is plus direction, it's not clear. So you have to make sure that quantum model of NPO is such that the observables of Alice, Bob, and Charlie, they are required to factorize. And your result will indeed, state will factorize according to these observables. And this is the final challenge that we had to overcome, that actually you can come up very easily from the original inflation hierarchy. There exist natural examples of mutually commuting observables on Alice's, Bob's, and Charlie's side, but let's focus on the Alice's side. And these are the observables that Nicolas was talking about, these joint measurements. And these observables, they give you such algebras, they generate such algebras that this generated algebra does not contain any non-trivial local observable. So now if your SDP gives you that, yeah, I have a state and I have these measurements, how I obtained this probability distribution, from these observables, you might not be able to say what is Alice's left side and right side of two copies that she had. And this motivated us then, and this is one of the final slides, that it motivated us to actually put in this distinction by hand, because we believe that there could be certain cases where this distinction from the original inflation hierarchy will be impossible to obtain. And then we ask MPO, instead of finding the full P of EM elements, we ask MPO to find the local generators in a way that whenever they sum up to the Schmidt rank R, they actually give you the original P of EM elements that you wanted to have. And this is the new hierarchy that we propose, that you always ask for such cases, and it's guaranteed for certain technical reasons of density that you will be able to always find such, if there exists such a P of EM, you will always find such decomposition into local cases, but you have to request it. And this led us to the final result that indeed, we can have a convergence that if MPO succeeds for n level of inflation, we know that there exists a quantum state rho that is symmetric over all permutations of n copies. This was already something that inflation gave us. Then later we used the definite theorem. And we showed that for n going to infinity, which is the inflating up to infinity, there also exists a product state such that you obtain the original distribution. And we are guaranteed to solve the approximate causal compatibility problem for any epsilon for large enough value of R. And now, if your MPO returns to be infeasible for a given R and for very large N, you can conclude that there exists no quantum model of the causal structure with measurement operators of rank R that produces these correlations P. So it still does not solve the original inflation conjecture, but it argues that you need this variable R. And yeah, this is the price to pay, indeed, that this additional parameter R that you have to keep, and the convergence for increasing value of R and N are indeed not monotonic, because if you increase N, you might show that you are incompatible, but if you increase R, you will be compatible again, maybe. So there is this non-monotonous convergence to the final result. However, if you let the R run to infinity, which is not feasible, obviously, on a computer, then the hierarchy in principle captures everything. So there exists indeed the converging hierarchy. And there are natural open questions then. What is the scaling of R for certain problems? Or can you other ways identify these local algebras? We argued that there could be a problem to find these local algebras, but it's not necessary that your SDP would ever reach these ways. It could be that you never get the Bell basis measurements as a result of your SDP. But because actually this example came from the Bell basis measurement, it was one of the first things that you consider, and you right away run into a problem. And then the big question is whether the original hierarchy is still convergent, and then how far one can go in the numerical methods. And this actually concludes the presentation. Thank you.
Thanks a lot. So maybe first I will start by some note for the online participant. It's easier if you ask your questions to everyone and not just to the computer of the speaker, because we don't have access to it. And we have 5 minutes for questions, so I don't know if someone has any question. And maybe I can start. Yes.
I can decide which one I like.
You should go down. This is old. Oh. This is old also. Well, we don't care. Well, okay. So I will start quickly by one question. So you say other ways to identify local algebras, and is the original hierarchy convergent? But is it completely necessary to identify the local algebras? And when you say, is it convergent, do you have an idea to what it could converges? And maybe the mathematical convergence theorem will not identify these local algebras. Don't you think it's a possibility?
So I think it's necessary to have, even to talk about according to what you factorize, no? You need to have some kind of distinction between Alice's two subsystems. And if it's impossible, okay, now I see your question. Okay. So I had a very impulsive, yes, sure, it's necessary, but I'll think about it. Wait. So you say that maybe there is some more abstract way that you can actually converge to the correct solution, but you can then translate this to the existence of this separation. Yeah, I don't know. I think that's a wild claim. I don't know how you would do that if you don't actually reproduce the local algebras, but you say that these kind of converging to certain result in SDP, certain maximization, implies that you actually have local separation between the states. That's a good claim, but I don't know how I would handle it, like how this translation would work. Yeah, okay.
Thank you very much for the nice talk. So for the 2-2-2-2 case, like the Bell scenario, there is this NPA hierarchy that people often use. So in that, we usually use pure states with projectors. So in this work, are you not using that, or the result is more general using POVMs?
So do you refer to the first part or second part?
In the second part.
So, I mean, this is a more general question, right? So you are given some arbitrary probability distribution. It's not 2-to-2 case. And also, I mean, you can, of course, use the numerics in the sense that you can use MPA hierarchy, but then the question is how far you should go into inflation, which becomes infeasible quite quickly, and also how large should be the rank of your measurements. That's also another question. And we had a master student working on this. I don't want to criticize his work, but I want to criticize more our work, that we gave him a task of writing this inflation hierarchy. And it was not so successful because, in a sense, it's not easy to, as soon as you need to have two inflations, high rank measurements, your dimension starts to explode right away. So it's not as easy just to use this small MPA hierarchy for a CHSH scenario. It's much more involving, unfortunately.
So thanks a lot for the talk. I have a question regarding the first part of the talk. So I don't really understand the meaning of this do operator in the quantum case. Like in the classical case, I have a feeling of that, like that you want to get rid of this part which affects the effect of A on B. But in the quantum case, like you have a shared quantum system, and then you force the party A to do something or to give some output. Then what's the physical meaning of that?
So maybe I can answer quickly scrolling up to show yet another analogy that maybe could be nice to see. So here I didn't emphasize much, but in the classical case, you are kind of tracing out the shared part system, right? You are tracing out lambda. So in the quantum, or you are taking the sum over lambda. In the quantum one, in the analogy, you do the same thing. So mathematically, you trace out the Alice's system. So you sum over all the possibilities there to make the link disappear from rho AB to A. But you can think of it in the following way, that in the lab, and that's how the experiment was also performed, that you can randomly decide whether to actually collect the statistics and make a measurement and send this outcome to Bob, or you can intervene on the Alice had made a measurement, she has her output, but you don't let Alice to send that. You randomly decide to intervene and just send something else to Bob. And this is like throwing away your classical data output. You are still intervening on the classical variable. And that's what's physically happening. Whether that fully captures the intervention or whether the true intervention is possible, that's a debatable thing. Because in classical way, you are intervening not on the output, but on the action, right? You are intervening whether a person smokes or not. In the quantum one, you are only intervening on the result because you cannot really force it to go a certain way, right? So then this is a debatable thing that maybe you can try to intervene on a channel or have some instrument that you force Alice to take certain quantum states there. So these are all the different questions that one could be considering there. And this definition that we have could completely be only one of the trivial cases of a more general picture. But thanks for letting me clarify this one more time.
Okay, so I guess this is the end of the morning session. So we have to come back at 1:45 for the afternoon session.
Thank you.